Shift gears a little bit today. We've been doing, the micrometers, the calipers. Yesterday we did the scales and meters, gauges. Today we're going to look at something really totally different. And we're going to look at the mathematics behind the resistor color code. So the resistor color code is a set of colors in order. It is black. Oops, I'm going to give myself a little more space here. Brown, red, orange, yellow, green, blue, violet, gray, white, and at the very bottom we'll have gold, silver, and then none. So these colors, this set of colors, first of all, you'll notice that starting here and going to about here, that is the colors of the rainbow: red, orange, yellow, green, blue, violet. We've tacked some colors onto the beginning and some colors onto the end to fill in some missing numbers. But a resistor, the color code of the resistor, has 4 distinct bands. The first 2 bands are digits. The third band is a multiplier. And the last band, the fourth band, which is usually spaced out a little bit further from the others, is a tolerance band or an allowance band. So the first 2 digits is what we'll deal with first. Actually, the third digit works the same as far as the colors are concerned, but its function within the number itself is different. So we refer to those first 3 as the main digits. So it's the 2 digits and the multiplier. So if it's in one of those locations, black would stand for 0, brown for 1, red for 2, orange for 3, yellow for 4. Green would be 5, blue would stand for 6, violet for 7, gray would be 8, and white would be 10. Gold is never used in one of those places unless it is in the multiplier place. In the multiplier place, gold is times 0.1, silver is times 0.01. So, in those first 3 digits, if we had, I'm trying to find a neutral color here so I don't confuse anything. I guess we'll stick with black. Let's say we have red, green, and then orange. Well, first we look up the colors and what they stand for. Red stands for 2, green stands for 5, and orange stands for 3. But now we have to use their position in this color code to assign them their value, their meaning. Remember, we said the first 2 bands were digits, so the 2 and 5 are digits. The third band is a multiplier. Well, that's not a multiplier by 3, it's 10 to the power of 3 is what that stands for. That is literally standing for 25,000. If we do another example, we might have yellow, blue, and gold. So here, yellow stands for 4, blue stands for 6, and gold, the only thing it can be in those first 3 bands is a multiplier. So it would be the multiplier. It is a 0.1. So this is 46 times 0.1, or 4.6 is what that's standing for. Most people are not aware that you can actually have decimals in your resistor color code. That is where the gold and silver bands come in, is to put those zeros into them. Next, let's look at the tolerance band. The tolerance band, there's actually only 6 different things that can be in that tolerance band. So I'm going to label here tolerance. If the gold stripe, the tolerance band is gold, that is a plus or minus 5%. If it's silver, it's plus or minus 10%. Those are both considered high quality electronics grade resistors, if those are low tolerance. Standard in the industry, if there is none, is plus or minus 20%. Now it could also be black. Black can sometimes be used for that tolerance band. That also signifies plus or minus 20%. Now again, in many standard electronics courses, they don't include brown and red tolerance bands. Brown tolerance band is plus or minus 1%. Red is plus or minus 2%. So it just goes off the same numbers as they had in their main usage. The brown and the red are military grade resistors. To be within plus or minus 1 or 2%, that's a pretty precise resistor. You hear talk about why is military supply so expensive. They talk about paying $1,000 for a nut and bolt. The reason for that is because they have these very high tolerances. And it's not necessarily that there is a more precise process for producing them. And there is a slightly better process for creating resistors that makes them more likely to be closer to the actual stated resistance with the color bands. But they still have a little bit, you can't get it to within a 2% tolerance. So what they actually do is they produce a bunch of resistors. And they might produce a batch of 1,000 resistors, let's say. Well, if their order is for plus or minus 1%, that brown tolerance band, they produce those resistors and they test them. And let's say after testing, of those 1,000 resistors, there might be 12 of them that pass, that are actually within that plus or minus 1%. So that they've produced 12 resistors that they can sell to that military contract. The reason military stuff is so expensive is the military still pays for the full 1,000. Even though they only 12 of them are good enough to use, the company had to produce 1,000 of them to meet that military contract. And in honest, most companies, at least the companies that I know of and that I have worked with that do military contracts, take a loss on the military contract. These 12 that they sell to the military, they lose money on. They take a loss on them. They do not pay for the full batch of 1,000. Where the company makes their money is they turn around and they have that batch of 988 resistors that did not pass the military specs, but are still actually higher quality than the standard market resistors. They turn around and they sell those then to other buyers as a very high quality resistor. It just wasn't good enough for the military contract, and that's where they make their money. Where the military really pays a steep price is when they order it's called proprietary parts, proprietary equipment. So it's something that is designed specifically for a military purpose. And not only is there not much of a use for it outside of that military purpose anyway, the military would not allow it to be resold because they don't want somebody else seeing that design. So where the company has to, they produce for the military contract, they fill the military contract, but any of those extra parts that didn't meet specs must be destroyed. So in that case, then the military does pay complete and full price for that whole batch, even though they only get a small percentage of them that passed. The company has to make money somehow. So anyway, let's take a look at how this all fits together then. Let's take a look at some examples. Now I'm going to draw my resistors vertical like this, just so I don't have to write sideways. And let's see, let's say we have violet, green, red, and silver. So remember, the first two bands are simply numbers, simply digits. Violet, if I remember, it stands for 7. It does. Green stands for 5. So that means 75. Red stands for 2. So if it was it's always that third number, that multiplier is always a power of 10 unless it's a gold or a silver. Then it is just times that decimal amount. This is 10 to the power of 2, so that's giving us 7,500. That would be ohms. Silver, in the tolerance band, is plus or minus 10%. So that's what that resistor is reading. So let's do white, orange, yellow, and gold. So again, we need the values for the first two digits, the white and orange. White is 8, orange is 3, so that's 83. Times 10 to the power of yellow is 4, so it's 10 to the power of 4. That's 830,000 ohms. Gold in our tolerance is plus or minus 5%. Now, we had talked earlier, a couple of weeks ago, about this being what is called a relative allowance or relative tolerance. Where the allowance, remember this is actually an allowance, even though the word tolerance is used for it quite a bit, is given as a percentage of that desired value, that base amount. So we can turn that into an absolute allowance. Turn that into an absolute allowance, we have to find 5% of that number. To do that, remember, 5% is 5 out of 100, and we know how much is that out of 830,000. If it ends up being 4,150, but let's take a check here. So 5 times 830,000, I should say, divided by 100, is 41,500. So we just cross-multiplied 5 times 830,000 divided by 100. 41,500 is that absolute allowance. That is, of course, in ohms as well. So the absolute allowance here, it's still 830,000 ohms is our desired value. But instead of plus or minus 5%, we can put in plus or minus 41,500 ohms. That seems like a large allowance, and it is. I mean, that to be off by over 40,000, yeah, that's a long ways off. But in most resistor applications, that's okay because the way we use the resistors negates that high error amount in the resistors. It's a little inefficient because it does dissipate a lot of power by using a network of resistors to guarantee a certain resistance. But it relieves the need to be more precise than that. That's why the military resistors have such a low relative allowance, is in order to be efficient and to minimize power loss, they need those more precise resistors so they don't have to build this intense network to try to cancel out any errors in those resistances. So in your notes, I would like you to try to find, for this resistor, we're going to have you find the absolute allowance. Colors in there in just a second. So let's do yellow, green, orange, and black or none for that tolerance band. So I'll give you a minute. Now remember, absolute allowance, that's plus or minus an absolute number, not a percent. So you got to use the percent first and use that percent to find that absolute allowance. So I'll give you a minute and then we'll go over this. Okay, let's take a peek here. So yellow is the number 4. Green is 5, so that's 45. Orange is 3, so that's times 10 to the third. That's giving us 45,000 ohms is our desired value. Black is plus or minus 20%. If it's black or no tolerance band, it's plus or minus 20%. So now we need to find what that 20% represents, how much that 20% is. The 20% of 45,000. Cross multiply and divide here, that comes out to be 9,000 ohms, of course. So the absolute allowance is 45,000 ohms plus or minus 9,000 ohms. Now again, you might be looking at thinking, these plus or minus 9,000 ohms, that is a huge allowance. And it is. I understand that. In fact, it looks even worse if we look at it in terms of that allowable range. So the allowable range, if you remember back to our precision measurement and allowance and error section, you take the desired value, in this case the 45,000 ohms, you subtract the allowance of 9,000 ohms to get a minimum allowable value of 36,000 ohms. We need to get the maximum allowable value, will be to take our desired value of 45,000 ohms plus that absolute allowance of 9,000 ohms to get a maximum value of 54,000 ohms. So you can see there that range, the acceptable or allowable range for that resistor, is from 36,000 ohms to 54,000 ohms. That's a huge range. Okay, so let's look at going the other direction. Now I realize Graydon and Mason, you guys have probably both done a little bit with electronics in your other classes. So I'm not going to dwell on this. I realize I'm rushing through this and only doing like one example of each type of problem. If you guys need more examples, please speak up. But I know you guys have had this a little bit in some of your other stuff. So what if I know the resistance and I need to code it on the resistor? Or I need to find a resistor that fits that desired resistance. So I need to know what code to look for. So let's say we know that we need 78,000 ohm resistor with a plus or minus 10%. First thing I have to do is I have to write this with 2 digits in front of the decimal point, and then the rest as, times 10 to the power of. So I'm going to keep the first 2 digits, the 78. My decimal point here started here, and it moved to here. It moved 3 spots. So that's going to be 10 to the third. I have to do 7, which is violet. 8, which is white. Sorry, 8 is not white. 8 is gray, if I remember right. Is gray. I don't know why I put 10 for white. That should be 9. 8 is gray, so I get that coded correctly. I think I did white for 8 earlier as well, so don't know why I messed that up today. Then 3 is our multiplier, 10 to the third, so 3 is orange. And plus or minus 10%, that would be a silver tolerance band. So violet, gray, orange, silver would be that color code. Or if we had a 0.39 ohm resistor, and we need it to be plus or minus 2%. So the 0.39, we're just going to do the 39 as our first 2 digits. Our multiplier is going to be this direction too, so that's going to be a 0.01. So 3 is orange. 9 is actually white. And our multiplier, 0.01, that's actually going to be the silver multiplier. Plus or minus 2%, that is a red tolerance band. So very, very small resistor, very, very tight tolerance. So now let's have to do a little math with this, obviously. Let's start off with a resistor that is 480,000 ohms, and we want it to be plus or minus 24,000 ohms. So in order to color code this, we need to convert this. This is now an absolute allowance. We need to convert it back into a relative allowance. We need to figure out what percent that is. Of course, percent is always out of 100. And we're going to put our allowance over here, 24,000, over our desired value of 480,000. And we will cross multiply and divide. So 100 times 24,000 divided by 480,000. Now you'll notice I just did 24 divided by 480 because I took the 3 zeros off the end of the numbers to save a little keystrokes. I get 5. So this is really plus or minus 5%. So we would code our resistor. 4 is yellow. 8 is gray. 3 zeros, so times 10 to the third, so the 3 zeros is going to be orange, is our multiplier, 10 to the third. And plus or minus 5% will be a gold tolerance band. So we can convert our absolute allowance into a percent allowance, or a relative allowance. The final step would be to take a range. let's say that we know we need a resistor that is in the range 5,200 ohms to 7,800 ohms. Well, we need to first find the desired value. The desired value is going to be at the center of that range. To find the center of the range, we're just going to add the two numbers together, 5,200 plus 7,800, and divide by 2. In other words, we're just taking an average. So we add those together, we divide by 2, that is 6,500 ohms. That is our desired value. Next, we need to find the absolute allowance. The absolute allowance is going to be found simply by taking the difference between this desired value and either of those numbers. It's easier to do it if I do the smaller numbers. The 6,500 minus the 5,200. That gives us 1,300 here. So this is a plus or minus 1,300. Of course, that is ohms as well. That is our absolute allowance. So then we need to turn this into a relative allowance. Well, we can color code it. So to do that, we're going to start off with our blank over 100, because we're looking for a percent. We take our absolute allowance, the 1,300, over our desired value of 6,500, and we will cross, multiply, and divide. 100 times 1,300 divided by 6,500. Giving us 20%. So this is plus or minus 20%. So what we're looking to color code here is 6,500 ohms plus or minus 20%. So again, this has to be written as 65 times 10 to the second. So there's 2 zeros at the end, or the decimal point has to move 2 spots, however you want to look at it. Plus or minus that 20%. So we start out, we're going to color code the 6, which is blue, 5, which is green, times 10 to the 2, well, 2 would be red, plus or minus 20% would be either no tolerance band or a black tolerance band. Either one works. So again, I realize I rushed through that and only did one example of each type, but I'm guessing I know you guys had a little bit of this in your other classes. You guys have any questions? Okay, so homework. Again, out of the book, on page 203, exercise 4.8, 1 through 29, the odds. Now, after today, we will once again shift gears completely. The rest of Unit 4 is algebra. So we're going to focus mostly on solving algebraic equations, a little bit on translating English phrases into algebraic expressions. That's about it. We're not going to get too big into operations with algebraic numbers or anything like that. But we do feel it's important for you to be able to solve equations. So that'll be the rest of this week, and then Monday through Wednesday of next week. And of course, next week, Thursday, will be our Unit 4 test already. We actually only have 3.5 weeks of this course left. We're done at the 12-week point with this class. So with that, you guys are free to use the rest of the hour to work on the homework here. I'll be on the network for a while if you guys have any questions or if you need